Let's talk about intersection and sum of subvector spaces. These are two well-known statements that we already mentioned in the lectures. So if V is a vector space and A and B are two subvector spaces, then we can consider A and B just simply as sets, and as such we know that the set-theoretic intersection of A with B, so A intersected with B, is always a subvector space of V. On the other hand, the set A union B is not in general a subvector space of V. Well, there is a very easy example already in R2. So if V equals R2 and A and B are two subvector spaces of dimension 1, a geometrical description of the situation is the following. So let's assume this is R2, V equals to R squared. And A and B are two one-dimensional subvector spaces which geometrically can be described as lines through the origin. So let's say this is A and this is B. Well, in order to show that the union of A and B, or to check the union of A and with B is a subvector space of R squared, we need to show in particular that there is a closure with respect of the sum. So if I take, for example, two vectors in the union A union B and I sum them up, I still get a vector inside A union B. Now let's take a vector here in A. Let's call it x1, and then take a vector in B which is not the zero vector. None of them is the zero vector, and we call it x2, and sum them up. Now we already have seen in previous lectures that the sum, geometrically, to reconstruct the sum of x1 and x2, it amounts to draw the parallelogram generated by the segments connecting x1 with the origin and x2 with the origin. So x1 plus x2, it is gonna lie somewhere here, which of course is not on A and is not in B. Therefore, it falls outside both A and B. So this shows that in general, the set-theoretic union of two subvector spaces is not a subvector space of V because it does not respect the closure with respect of the sum. Let's ask then, what is the closest subvector space of V to the union A union B? So we know that the smallest subvector space generated by a set is being denoted like this, and it amounts to take the set of linear combinations of all the elements in this set. In this set in particular, the set is A union B. Therefore, the closest of vector spaces to the union of A and B is the vector space generated by A union B. Now, in general, this vector space is denoted by A plus B. And A plus B as a set can be also described as the set of vectors which are represented as a sum of an element of A plus an element of B. After this introduction, let's now consider some numerical example. So let's find the intersection and the sum of two subvector spaces of R3. The subvector space A is given by xyz in R3 such that this linear equation is satisfied, 2x minus y minus z equals to 0. Therefore, we are expressing A in the form of exercise 1.1, and then we also express B in the same form, but the vectors of B are going to satisfy a different equation from the previous one. Now in exercise 1.1 we have checked that these two sets, A and B, are indeed subvector spaces of R3. In the same exercise, we also provided a way to get a basis for each such subvector space. Let's use the same procedure here. So from the equation defining A, we get z equals to 2x minus y, so that we can write A in the following form: x, y, and then instead of z, we will be imposing this relation to x minus y, and then there are no more other relations that have to be satisfied by these vectors in R3. Now, therefore, we can derive that the vectors 1, 0, 2 and 0, 1, negative 1 is a basis for A, because as shown in the exercise 1.1, we have seen that in turn, considering x equals to 1 and y equals to 0, and then x equals to 0 and y equals to 1, we get two linearly independent vectors, and they provide the basis of this subvector space. Similarly, we have that B can be expressed as x and then 3x minus 2z and z, where 3x minus 2z comes from the equation 3x minus y minus 2z equals to 0 that has to be satisfied by the coordinates of elements in B. So we can explicit y in function of x and z, and then impose the condition here in the very writing of B. So that the vectors 1, 3, 0 and 0, negative 2, 1 form a basis for B. Now, the two free variables in the description of B are x and z, so alternatively we take them to be 1 and 0, and we get these two vectors. I'm going to show now the geometrical representation of the situation we are analyzing algebraically. So what we are seeing here is the big vector space V, which is R3 in our case, and we will be seeing now appearing the subvector spaces we are considering. First, the subvector space A, here it is. So you see it is like a two-dimensional subvector space, is like a plane in R3. The plane is tilted in all the axes, as you can clearly see here. These are the vectors of the basis we just derived for A, and we call the vectors u and v. So v is 1, 0, 2 was the first vector of the basis of A, and u is 0, 1, negative 1 is the second vector of a basis of A. And we check geometrically if u and v is indeed a basis for the subvector space A by taking a certain number of linear combinations of u and v and see if they all fit in the plane that we just draw. Okay, so if here there are a few thousands of them, and from this angle we cannot see if they all lie on the plane, but if we just scroll the point of view around, we can clearly see that they are all lying on the plane. So that is the evidence of the fact that indeed u and v are linearly independent, and they are a basis of the plane A, the subvector space A. Now let's see the other two vectors of the subvector space B. Here are denoted as A and W. So W is the first vector of the basis for V, so is 1, 3, 0, and A is the second vector, which is 0, negative 2, 1. What does the B-plane B subvector space look like? Well, it looks like another plane passing through the origin, and we see it represented here now. It is in green, and the linear combinations of A and W, a few thousands of them, are the one that just appeared now, and as you can see, they all belong to the green plane, so to the plane B. Therefore, just as before, that is an evidence that W and A form a basis for B. Summing up, we have the following subvector space expressions that we considered so far, and these are essentially all of them. We have one that we will call expression in coordinates, and the second one, which we will call parametric. And coordinates for A is the representation in which we actually see the coordinates of the vectors belonging to A. So here, when we describe this way, you open the curly brackets to indicate the set, A as a set. Okay, so this is why we call it in coordinates. On the other hand, here we denote A by means of a set of generators, actually a basis of A in this case. We just indicate two vectors of A from which we can derive all the other vectors. And similarly for B, the coordinate representation is the one that describes B as a set of vectors in R3 satisfying a certain homogeneous linear equation, and the parametric is once again providing a basis for B, so representing B as the vector space generated by two vectors in this case, since B is a plane as dimension 2. Each of these representations has its own advantages and disadvantages. For instance, if you want to check that a certain number of vectors belong to A or don't belong to A, certainly the coordinates representation of the subvector space is much more useful, because you just have to plug in the coordinates of the vectors you have and see if this equation is satisfied or not. So for the computer it's much easier to do that if the subvector space is represented in coordinates. On the other hand, there are certain, as we will see, there are certain situations in which it is better to have A represented through the parametric expression, because in a sense we are just carrying with us just two vectors of A and then recovering all the others as linear combinations of these two vectors. Therefore, we pose ourselves the following question: which expression is the best to write the intersection and the sum of vector spaces? For the expression of an intersection, we can say that if A and B are both expressed in coordinates, then the intersection A with B is the set of vectors satisfying both defining conditions simultaneously, the defining conditions describing A and B. So in this case, we have the following representation of the intersection, again in coordinates. A intersected B equals the set of vectors x, y, z in R3, such that at the same time 2x minus y minus z equals to 0 and 3x minus y minus 2z equals to 0. This we have seen already in the exercise 1.2, this writing, and we have shown there that this is a vector space. Now, if A or B is in parametric form, then the expression of the vectors, the intersection A with B is much more complicated to express. Therefore, I suggest to express the one that are in parametric form in coordinates, and then to write the intersection, as we just did here. An altogether different situation is for the sum. Unlike the intersection, the sum a plus b is more easily expressed when both a and b are in parametric form, because in that case we can certainly express a plus b immediately in parametric form as well, just taking as a set of generators, in this case, the union of the bases or generators of a and b. Therefore, we can write a plus b equals the vector space generated by the set of these four vectors, the first two of which is the basis for a, and the second two is the basis for b that we just considered. Now, of course, we're in R3, and we have four vectors in R3. Therefore, these can just be a set of generators, and they certainly will not be linearly independent because of the basis extension theorem. The next issue is, once we have expressed the intersection and the sum of two subvector spaces, how do we actually understand what they look like? So understanding A intersected B and A plus B. From the writing of A intersected B in coordinates, we can determine its dimension by means of the RC theorem as explained in exercise 1.2. Essentially, this is A intersected B is the set of solutions of the following system of linear equations. Therefore, the RC theorem tells us that this set of linear equations being homogeneous will always have solutions, and the dimension of these solutions is going to be to the number of the unknowns, which is 3 in this case, x, y, and z, minus the rank of the incomplete matrix. Now the number of unknowns, as we said, is 3, and the rank of the incomplete matrix, it is the rank of this matrix, the one that has as a first row 2, negative 1, negative 1, and second row 3, negative 1, negative 2. These are the coefficients of this system of linear equations. Well, the rank of this matrix is obviously 2, because we can see that the second row is not a multiple of the first, so the first two rows are linearly independent. Therefore, we have 3 minus 2 equals to 1. So the dimension of the intersection is 1. So it's going to be drawn as a straight line passing through the origin of R3. Now we know just the dimension. How do we find the basis from the expression in coordinates of the intersection? Well, we can in turn implement the conditions that we have here, that we have two of them in this case, in the writing of the generic vector of the subset of the subvector space. So if we implement in the writing of the generic vector the first equation, we will end up with this expression. So A intersection B equals to the set of vectors of the form x, comma y, comma 2x minus y. Because from the first equation we can express z in function of y and x, and write z equals to 2x minus y. So z is going to be 2x minus y in R3. But these are not anymore unrestricted vectors, because there is still the second condition that has to be satisfied, and the second condition reads as 3x minus y minus 2z, but we already expressed z in function of x and y, so z we can write in the expression what it is, 2x minus y equals to 0. So this is a writing of A intersected B, which implements the first condition of the two. Now, just expanding this equation, we will end up having just the following equation, y equals to x, from this equality. And then the next step is implementing this condition, imposing this condition in the writing of the generic vector, so that y equals to x here becomes x, and then if here we write y equals to x, this will also become x. Therefore, A intersected B is going to be the set of the vectors of the kind x, 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 which is simply the vector space generated by the vector 1, 1, 1, and these constitute a basis for the intersection. Let's see how we draw the intersection in the geometric situation describing the two planes, the two subvector spaces A and B, and the respective bases. So as you see, now there is a straight line passing through the origin, this gray one, and it is generated by the vector 1, 1, 1. Unfortunately, the rendering is not accurate in the intersection, therefore it looks like that the straight line doesn't actually lie in the intersection of two planes, but this is an error of the program in rendering the two planes. So this straight line should actually be in the intersection of these two drawn planes. So we can pan the point of view around the z-axis and see how it looks like. So you see that is the one-dimensional subvector spaces that represents the intersection of A and B. Now we consider the union, now we consider the sum A plus B. Let's see how to find the dimension of the vector space A plus B. Now there is a very important theorem that applies particularly in this situation. Theorem relates the dimensions of the following four subvector spaces of a vector space V. Namely, the subvector spaces A, B, A plus B, and A intersected B. The theorem goes under the name of Grassmann theorem and reads as follows. The dimension of the vector space A plus B is going to be equal to the dimension of the subvector space A plus the dimension of B minus the dimension of the intersection. Now here we can squarely apply the Grassmann theorem and derive the following result, that the dimension of A plus B is going to be equal to 3 because dimension of A is 2, dimension of B is 2, and we have just proven that the dimension of the intersection is 1. So 2 plus 2 minus 1 is 3. So being the dimension of A plus B 3 and being A plus B a subvector space of R3, that means that A plus B is going to be the whole R3. And if we want a basis of A plus B, then we can simply take the canonical basis of R3, E1, E2, E3, where E1 is 1, 0, 0, E2 is 0, 1, 0, and E3 is 0, 0, 1. Let's see, however, how to find an explicit basis of A plus B in the general case when we don't know that A plus B is all Euclidean vector space. So in general, for a general subvector spaces AB in Rn, A plus B is not going to be equal to Rn. And a basis can be extracted from the generators appearing in the parametric expression of A plus B. Let's see, for example, in our exercise, the generators are the following ones: 1, 0, 2, 0, 1, minus 1, 1, 3, 0, and 0, negative 2, 1. The first two were the basis for A, the second two the basis for B. So these are the generators for A plus B, as we've seen already. Now they are not a basis because there cannot be four linear independent vectors in R3. But we can start from them and operate in a certain way to see which one of these four constitute a basis for A plus B. We basically have to take three linearly independent vectors inside these four. How do we do that? Well, we can actually construct the matrix for which these vectors will be column vectors. So let's consider this matrix for which the first column vector will be 1, 0, 2, the second column vector will be 0, 1, negative 1, the third 1, 3, 0, and the fourth 0, negative 2, 1. We call this matrix M, and we operate with row elementary operations. It is very important that we are operating with the row elementary operations, and we construct this matrix by taking our vectors and writing them as a columns of the matrix. Okay, this will not work if we constructed the matrix writing them as rows instead of columns and then operating on rows. So we have to operate with row elementary operations on this matrix constructed putting the vectors as columns. Okay. Now the first row elementary operation is described here, and we will be getting this matrix. So we just killed the 2 here using the 1 up in the first row, and then to reduce further in echelon form this matrix, we have to kill this negative 1 here in the third row, and we will be using the second row this time. With this elementary operation, we will be getting this matrix. Now, from general theory of row elementary operations, we know that the rank of this matrix is exactly the rank of the initial matrix M. Not only this, but also that all the linear relations of the column vectors are respected. So now what we see here, we see that the first 3 vectors are linearly independent because they constitute an upper triangular matrix, and the elements along the diagonal, they are all different from 0. So the first 3 vectors are linearly independent, and therefore we conclude that the fourth vector is a linear combination of the first 3. While the same then is going to be true for the vectors of the initial matrix M. So the fourth vector is going to be a linear combination of the first 3. Now, therefore, since the first 3 vectors of the matrix M are linearly independent, there will certainly be a basis, because there cannot be more. We already know that dimension of the sum is the dimension of the sum of the vector space is 3, so we are looking for 3 linearly independent vectors. So then we can take the first 3 of them. We could have as well taken the first, the second, and the fourth. That would have made it also a basis. So this allows to derive, without actually knowing that a plus b is the whole R3, deriving an explicit basis for the sum of the vector space sum of A and B.